Welcome to solverfy.
Okay, problem 28.6. We have 2 point charges of positive charge of certain values, and they're moving in different directions, and they're a certain distance apart from this point P. So first question is, when two charges are locations shown in a figure, what are the magnitude and direction of the net magnetic field they produce at point P? Okay, so we're going to start off with writing the magnetic field of a moving point charge. So we have B, and then at point P, we're going to write is equal to mu naught over 4 pi. And then I'm going to write down 1 over distance squared. And that's going to be similar between the two different terms. So we have a term that's for the positive charge q and one for positive charge q prime. And then in brackets, I'm going to put down what the difference between those terms are, because it's the same. We're going to write down what's different, and then they're just going to be added together. So one is going to be the charge times the vector v cross r hat. So for the first one, we have q v, and then it's going to be the unit vector I hat cross with negative j hat. So I hat cross with negative j hat. That's the vector unit vector for the velocity crossed with the r hat vector extending from the point q to b. Okay, and then that's going to be added to q prime v prime charge velocity, and it's going to be negative I hat, it's going left, crossed with positive j hat. So negative I hat crossed with j hat. Okay, so then that's going to then be equal to the same constants, mu naught over 4 pi over d squared. And it's going to be the numbers we have here. So it's going to be 8. Now I'm just going to rewrite this. So q v I hat cross negative j hat is going to be negative k hat. And then plus q prime v prime. And then we have negative I hat cross j hat. That's going to be, again, be negative k hat. Okay, so then all this is numbers, and then we have the negative k hat for each of them. So if you solve that, we get 437.5 micro Tesla, and then negative k hat direction. Okay, so that's part A. Part B was magnitude and direction of electric and magnetic fields exerts on each other. Okay, so first off, I'm going to start with the next page. So we have the force, the electric field of Q acting on Q prime. That's going to be 1 over 4 pi epsilon naught, and then Q prime Q over 2d squared. 2d is the distance that separates them. Q prime times Q, this is just Coulomb's law. Okay, so then that's just all calculated out. That's all numbers we have. So 3.74 newtons. And then we have to figure out what the direction is, and that's going to be negative j hat. So if we go back to the first page, Q acting on Q prime, those are both positive charges. It's going to repel. Q prime is going to be pushed down, which is negative j hat. Okay, and then due to symmetry in the calculation, the force of the electric field, Q prime acting on Q, it's just going to switch those two, Q and Q prime, but that's going to be the same value. So then we just get 3.74 newtons in the positive j hat direction. So the So the top charge is going to be repelled, pushed up. Okay, so how about the next one? So force of, due to the B field of Q acting on Q prime. So this is going to be a Lorentz force law. So we have a moving point charge Q prime, V prime vector, crossed with the B field of Q acting on Q prime. So the Lorentz force law Q V cross B. So we can plug this in. So we have Q prime, V prime, and then the V prime unit vector was the negative I hat. That's going to be crossed with the magnetic field of Q acting on Q prime. So we've already shown this before. So that's going to be mu naught, or 4 pi, 1 over 2d squared. So it's 2d instead of d now, because that's the distance away that the Q prime is from Q. So it's going to be the same thing, except it's going to be 2d squared here. Okay, then we have QV and then negative k hat. So very similar to the part A that we did. Okay, and so that's going to be all numbers, and then simplified down to 1.687 millinewtons. And then negative I hat cross negative k hat is going to give us negative j hat. Okay, so then we can do the same thing for the force B, Q prime acting on Q. So again, Lorentz force law, but due to symmetry in the calculations, we're going to get 1.687 in the millinewtons in the positive j hat direction. Okay, and so we are then asked what the ratio is between the magnitude of the electric force and magnitude of the magnetic force. So we can just simply write down the ratio is equal to the force electric over the force due to the magnetic field. So basically this is Coulomb's law versus our Lorentz force law. Then we just write down, since these are the same value for each of them acting on the other, so the force due to the electric field is going to be 3.74 newtons compared to 1.687 millinewtons, and that's going to be a ratio of 2:17. So we see that the electric force, the force due to Coulomb's law, is going to be much higher. It's going to be 2,200 times as strong. Okay, so then what's the final question? If direction of V prime is reversed, both charges are moving in the same direction, what magnitude and direction of the negative forces that the two charges exert on each other? Okay, so since all that change is the direction that's on of the second charge, it's going to move to the right now. The magnitude at that instant that they're this far apart is not going to be different in the force and the magnetic force. What's going to change is the direction that is different. So Coulomb's law is going to dictate that they're still going to be repelled. The electrical force is still going to repel them, but the magnetic force is the question here. So what's going to happen there? So if we write down what those are, so we have BQ prime acting on Q. That's going to be k hat. So Q prime acting on Q, that's going to follow right hand rule. That's going to be a magnetic field out of the page here. So that means that when Q is moving to the right, that's going to be I hat crossed with K hat. And it's going to result in a force that is negative J hat. So that one's going to be pulled down. And due to a symmetry of arguments here, Q prime, the magnetic field of the point charge Q acting on Q prime, that's going to be negative K hat. And that means that we have I hat crossed with negative K hat. And that's going to result in positive J hat. So that means that these two charges, the magnetic field is going to cause them to be forced towards each other. However, we saw that the ratio of the Coulomb force to Lorentz force is going to result in them actually being repelled, and this is 2200 times stronger.